Hello, everyone. Today, in the evening session, we have a presentation from Assistant Professor Dr. David Rounce. He is an Assistant Professor at Civil and Environmental Engineering at Carnegie Mellon University, USA. Before starting presentation, I would like to say a little bit about his bio. He is a assistant professor. He joined the Civil and Environmental Engineering Department at Carnegie Mellon University in 2020. He received his BS in Civil Engineering in 2010 from Villanova University and his master degree in Environmental and Water Resource Engineering in 2012. And he did PhD in Civil Engineering in 2016 from the University of Texas at Austin. He conducted postdoctoral research in the Glacier groups at the University of Alaska Fairbanks. So we are going to hear about like global glacier loss projection from his presentation. So David Rounce, floor is yours.
Great. Thanks, Mellon.
Yeah.
And thanks everyone else for having me here. I really appreciate it. Sorry that I can't be there in person like I was for the first few days. So today I'm going to talk a bit about some of the recent projections work that we published in a paper in Science earlier this year. And then I'm also going to share some newer work that we did specifically for the State of the Cryosphere report that took projections out to 2300. And that include a lot of additional work by Fabian Massillon, Lillian Schuster, Brendan Tober, and Matthias Huss. So let's dive in. So we know that glaciers are responding to climate change. Here we're seeing a rendering of changes for Rhone Glacier in Switzerland from 1850. And here you can see 2000. So you can see that the glacier has retreated considerably and the glacier has also thinned considerably. And this is true for marine terminating glaciers around the world as well. So here's an example of John Muir Glacier in Alaska, a photo from about the 1940s and the same photo in the 2000s. Once again, you can see that the glacier has retreated substantially and has also thinned where the ice is further back. And then this is where I did my PhD work, Imja Glacier in the Nepal Himalayas. Here's a photograph from 1955. And here's another photograph from the mid-2000s. You can see not only has the glacier thinned, this is a debris-covered glacier, but we also have the formation of a glacial lake, which can be a potential flood hazard for downstream communities. So we know that the glaciers are responding to climate change, and this is true really for all glaciers globally, whether it's in Greenland, in Antarctica, in Africa, in the United States, in the Andes, in the Arctic, in Alaska, in the Everest region, and high mountain Asia. Really, glaciers all around the world are retreating. And the impacts associated with that are really vast. It includes things like sea level rise, the destabilization of surrounding terrains, leading to rockfalls and avalanches. It includes aspects of water resources and their effects on being able to provide a consistent flow for hydropower. The same thing for potable water and irrigation. And as these glaciers retreat, they're also prone to form these glacial lakes, which can be flood hazards. And so really, regardless of whether you live in the coasts, whether you live in the high mountains, or if you live anywhere in between, it's more than likely that the glaciers are going to impact your life in some way in the future if they're not impacting you already. Now, one of the major advances over the last couple of years has really been an unprecedented ability to monitor glacier changes. This was a study that was published by Roman Huguenet, or led by Roman Huguenet back in 2021. And what's really exciting about this research is they measured the mass change of every glacier globally. So all 216,000 glaciers, they measured how much the glacier had changed between 2000 and 2019 for all of them. And what it did was it provided us with a really detailed picture of the spatial variations in glacier mass change. And so you can capture things like in high mountain Asia, you can see the Karakoram anomaly where you have these yellowish and bluish colors here. It was a period where there was about neutral or sometimes slightly gains in mass change compared to, for example, the rest of the Himalayas, where you start to see a lot more mass loss. You also capture, for example, in Southeast Alaska, some of the highest rates of mass loss, right? And so you can start to look at these spatial distributions, and now we can incorporate those into our models by using this data for calibration. So I'm going to jump right into the results, and the results are quite staggering. So what we did was we ran our model for various shared socioeconomic pathways, or SSP scenarios, and then we aggregated those SSP scenarios into different temperature change scenarios, into 1.5 degrees, 2 degrees, 3 degrees, and 4 degrees. And so on the figure in the top left, you're looking at the mass change, so the percent that's remaining over time from 2015 to 2100. So the blue line is showing you the mass that's remaining for 1.5 degrees scenario, and the red line is showing that for plus 4 degrees. And so you can see that we estimate that the mass remaining will vary somewhere between about 25% losses, so about 75% of the ice remaining. And for a higher scenario, you're looking at losing about 40% of the mass, or having 60% of the global glacier mass remaining by the end of the century. Now, the story is a little different when we think about the number of glaciers. By number, we're projecting that we'll lose on the order of about 50% of the glaciers, even in a best case scenario. So we're going to lose a lot of glaciers, even if we're able to limit that temperature increase to 1.5 degrees. But we can lose over 80% for those higher temperature change scenarios. And so you're talking about the difference of 30%, 20 or 30%, if we're able to really move away from those 3 degree scenarios and keep that temperature change scenario to 1.5 degrees. And the reason why we have this difference between the amount of mass loss versus the amount of glaciers lost is because most of those 216,000 glaciers in the world are small. So they just don't have the ability to withstand the increases in temperature. Now, as I mentioned, we looked at the mass change. One of the reasons that we focus on mass change is because glaciers are one of the largest contributors to global mean sea level. And so we see that every increase in temperature is really critical for sea level rise. So we project, the plot that you're looking at here is the cumulative glacier contributions to sea level rise from 2015 to the end of the century, again, for those various temperature change scenarios. And you can see that for 1.5 degrees, we're looking at the glaciers contributing on the order of 90 millimeters, while for those higher scenarios, when we get into 3 degrees, when we get into 4 degrees, we're looking at the glaciers contributing about 130 to 150 millimeters. So we have the ability to limit a lot of the glaciers' contributions to sea level and recognize that the glaciers are just one of the many contributors to sea level rise, right? Along with the ice sheets, along with thermal expansion, for example. Now, when we look at how the glaciers are responding to temperature increases, it really depends on the region. So for a lot of the small glaciarized regions that I highlight here in Central Europe, the low latitudes, New Zealand, the Caucasus and Middle East, a lot of these smaller glaciarized regions, they're incredibly sensitive to differences between 1.5 degrees and 3 degrees. And the reason being is that when you get to 3 degrees, these plots are showing you the mass remaining at 2100 on the y-axis for different global mean temperature change scenarios. When you get to 3 degrees, you've almost lost all of the glaciers in these regions. So you've completely deglaciated the mountain ranges in these regions. And so the difference between 1.5 degrees and 3 degrees, in many cases, is preserving the ice that remains here. And these are areas where a lot of people live and interact with these glaciers. They're an important part of the cultures. They're an important part of the tourism of the countries and the communities surrounding them. If we look at some of the larger regions, so here focusing on Alaska and the Antarctic and subantarctic peripheral glaciers, we see a little bit different of a story. And we can see that there's roughly a linear fit. So as you increase the temperature, we see that we just get more mass loss, or we have less glacier mass remaining at the end of the century. And what that means is that any reduction in global mean temperature is going to preserve a lot of the ice. And that's the same signal that we see at the global scale. Now, as I mentioned, one of the exciting things with our study was that we had this very detailed and complete picture of the glacier mass change for every single glacier that we use for model calibration. And this enables us to start to look at the spatial distribution of the glacier mass loss, or in this case, the glacier mass remaining at the end of the century relative to present day. And so the bluish and yellowish colors are showing you where we have more than 50% of the glacier remaining at the end of the century. And the reddish colors are showing where you have about less than 10 to 20% of the glacier mass remaining. So we're talking about 80 to 90 to 100% glacier mass loss in those regions. And if the area experiences complete deglaciation, that's shown by these white circles that are outlined in black. And so you can see here for 1.5 degrees, we have some yellowish and bluish colors, for example, in the Karakoram and High Mountain Asia. We have higher rates of mass loss. So we see some areas that are experiencing near complete or complete deglaciation, or on the order of 70-80% mass loss. Same thing that happens in southeastern Alaska, where we had some of those highest rates of glacier mass loss in present day. And you can see this is for 1.5 degrees. For 2 degrees, you see that we start to get a lot more red color, so we're losing a lot more mass. We see that we start to have a lot more black circles showing deglaciation, and that really increases for 3 degrees and 4 degrees. So I'll flip through that again. You can see that the widespread loss and the deglaciation really becomes apparent when we get to those higher temperature change scenarios. Now we can also focus on the tropical glaciers. And it's important to understand how do our projections compare to previous studies, both compared to the glacier model intercomparison work that was led by Ben Marzayan, as well as some previous work that's been used to project further out. For the tropical glaciers, we find that even with 1.5 degrees increase in temperature, we expect that there are still going to be severe losses. Fortunately, this is actually slightly less than had previously been projected. So we're still looking at the glaciers losing between 70 to 90% of their ice by the end of the century, depending on that temperature change scenario. But we're talking about being able to preserve a lot of ice, more than 10%, 15%, 20%, depending on the scenario. We can preserve that amount of ice if we can limit that temperature increase to 1.5 degrees. The other thing that I'll show, and these are newer projections, as I mentioned, that are done by 3 glacier evolution models. They were done specifically for the State of the Cryosphere report. And you can see that the projections now go out to 2300 because the glaciers are going to continue to respond to those increases in temperature beyond the end of the century. They're still going to continue to change. And what we see in the tropics is that the glaciers can actually start to slowly recover beyond 2080 for some of those low warming scenarios. So if we're able to limit our temperature increase to 1.5 degrees, we might actually have a positive change after 2100, where we can start to grow back these glaciers that are such an important water resource and an important cultural aspect for many of the communities in these tropical areas. For mid-latitude glaciers, here showing the southern Andes, Western Canada, the United States, Scandinavia, New Zealand, the Caucasus and Middle East, and Central Europe, we see very severe losses even at 1.5 degrees, just like the tropical glaciers. In the southern Andes, we're looking at losing approximately 40% of the glaciers in a best case scenario to upwards of 70%. In some of the smaller glaciarized regions, as I mentioned, Western Canada and the US, Central Europe, we're looking at the difference between losing about 80% of those glaciers to 100% of those glaciers for those higher temperature change scenarios. And these losses are a little bit higher than previous projections. Now, when we look at, again, going beyond the end of the century for these temperature change scenarios, And when we look at this through 2300, again, we start to see in some areas, the areas that really are prone to potentially losing all of their ice, Western Canada and the US, Caucasus and Middle East, Central Europe, we see that, again, slow regrowth for some of these regions after 2100. And then when we think about the Southern Andes, one of the larger regions that we're showing here, we see that 1.5 degrees or 2 degrees will enable these glaciers to really start to reach a new equilibrium and stabilize. So the mass change between 2100 and 2300 is very little, or it's actually not going to change, right? So they're still going to lose 40 to 60% of their mass, but they're not going to lose an additional amount beyond that, which is very important. We can limit that mass loss if we're able to limit our temperature increases to 1.5 degrees. And the last region that I'll show are the polar regions and high mountain Asia. I haven't shown all of the cryosphere regions. You can see those in the State of the Cryosphere report. Here I've just selected some Arctic regions as examples: Iceland, Alaska, Arctic Canada South. You can see that for these Arctic regions, we're looking on the order of, again, losing between 40 to 60% of the glacier mass over by the 2015 to 2100 for those different temperature change scenarios. Right? So again, we have a very big impact going between 1.5 degrees and some of those higher temperature increase scenarios between 3 and 4 degrees. For high mountain Asia, we see a pretty diverse picture. So in Central Asia and South Asia West, where you have some of the larger glaciarized areas within high mountain Asia, you have the Karakoram, for example, we start to see that in these areas, they're going to lose on the order of about 50%, 40 to 50%, even in that best case scenario of 1.5 degrees, while they'll lose a little bit more than 60 to 70% for those higher temperature change scenarios. Again, we can preserve a lot of the ice and avoid a lot of the worst impacts associated with these glacier changes if we're able to minimize the temperature increase to 1.5 degrees. South Asia East, which is home to the Himalayas, this is a little bit of a smaller region compared to the rest of high mountain Asia, and we see that the picture is a lot worse. We're looking at losing about 70% of the glacier mass by 2100 in the best case scenario, and upwards of 90% in some of those higher temperature increase scenarios. Now, again, as we move out to 2300, we actually predict faster glacier mass loss in many of the regions in the polar regions and in high mountain Asia compared to those previous studies. And when we go beyond 2300, for many of these regions, we're starting to see that if we can limit our temperature increase to 1.5 degrees, in some of those low warming scenarios, we'll actually see regrowth of glaciers beyond 2100 through 2300. And in others, when we get into that 1.5 degrees to 2 degrees, we see a bit of a stabilization. Again, very, very important that we limit that temperature increase so that we allow these glaciers to stabilize beyond 2100 and don't continue to have that considerable glacier mass loss. Now, as I mentioned at the start of the talk, these glaciers are a very important water resource. So predicting how that glacier runoff is going to change in the future is very, very important to many communities around the world who rely on these glaciers for water. And so we can think about this in two ways. We can think about this on an annual time scale. And when I think about this concept of glacier runoff, we refer to a concept called peak water. When is the most water that we're going to have from these glaciers? So if you think about these glaciers as a reservoir and you have control of the floodgate to open and close it, really what happens is that when you start melting the glaciers a lot, you're essentially opening the spillway. You're opening that floodgate and you're releasing a lot of water downstream. So you're actually going to increase the amount of glacier runoff that you're going to have. But because you are releasing a lot of water in your reservoir, eventually you're going to get to the point where you don't have enough water to be able to continue to release. And so you're going to see this reduction in runoff in the future. And when that occurs, when you have that peak water, that maximum amount of glacier runoff, we refer to that as peak water. Now, if we look at this on a seasonal time scale, right, What we know is that these glaciers provide a very important buffer against droughts in many regions of the world. And so, for example, the Maipo Basin in Chile that provides water to Santiago, there was a mega drought a couple of years ago. And at that time, the glaciers were estimated to contribute approximately 40% of the water resources to Santiago. So again, these glaciers can be a very, very important water resource, especially at the end of summer, once you've already had the snow melt, and in many regions of the world where you have less rainfall. And so what happens is, again, with peak water, you're going to see this increase in water resources, even at the summer, end of summer months. But then you see a very strong reduction once you've really already melted away your glaciers, and then you have this big issue. Now, peak water is highly dependent on the watershed. So here I'm showing many watersheds in high mountain Asia and showing different plots. These are shown, the color lines are showing for shared socioeconomic pathways. So for 1.-2.6, we're looking at some of those lower temperature change scenarios of 1.5 degrees to 2 degrees. For SSP 585, we're looking at higher temperature change scenarios on the order of 4.5 to 6 degrees. Now, I'll highlight two basins here just to show the differences. The Brahmaputra, this is an area that's already been experiencing considerable glacier mass loss in Southeastern Asia. What we project is that they've already hit peak water. So the amount of glacier runoff that's available in the future is only going to continue to decline. And so we're looking at a change in glacier runoff, a relative change, where by the end of the century, they're going to have about 20% less glacier runoff than they do at present day. And what that means is that communities who rely on this water are going to need to either conserve 20% of their water resources, or they're going to have to find alternative sources of water. For example, groundwater, which is already having challenges in these regions as well. If we look in a larger glacierized area, like the Indus River Basin, we see that there is a lot of ice. And so peak water hasn't occurred yet. But how much, when peak water occurs and how much that increase in peak water is going to be compared to present day is going to depend on that temperature change scenario or that emission scenario that we are able to choose as a global society. And so you can see that if we're able to limit our temperature increases, limit our emissions, that peak water will peak around 2050 before it'll stabilize. While if we have some of those higher emissions, higher temperature change scenarios, we project that peak water will occur around 2070. So there's going to be more water in these river basins in the middle of the century before we start to see a decline. Now, in Europe, just as another example, we find that all of the watersheds, they've already passed their point of peak water. So we're seeing reductions in future glacier runoff on the order of 30% by the end of the century relative to present day. Again, it's going to be the loss of very important water resources. And similar trends of already having passed peak water are observed in South America as well. Now, it's not just water resources that these glaciers provide, as well as contributions to sea level rise. A lot of these glaciers are embedded in our lives. And so if we think about some of the iconic peaks or treks around the world, they're also going to change. And so here's an example of Khumbu Glacier, which flows off of Mount Everest. The plot that you're seeing in the top right is a cross-section profile. So you're looking at the elevation where the highest Mount Everest is located in the top left of your figure, and Down Glacier is located on the right. And what it's showing here is what the glacier will look like at the end of the century for different temperature change scenarios. And it's a little bit hard to see these differences, so we're going to zoom in on a section. Specifically, we're going to zoom in on the Khumbu icefall. And so here you can see that for 1.5 degrees, we project that ice will actually still flow through the Khumbu icefall and roughly end at where present-day Everest Base Camp is. While for those higher temperature change scenarios, we're actually going to see the ice retreat. The glacier is going to retreat above the Khumbu icefall. So you're going to have a deglaciated Khumbu icefall. In some cases, this is one of the most hazardous beyond being at very high elevations, this is one of the most hazardous spots along the entire trekking route of Mount Everest. However, when you remove these glaciers, you're also going to have a lot of destabilization of the surrounding terrain. So it's likely going to be still a very hazardous area. But think about this. This is one of the most iconic parts of the world, the highest, the tallest mountain in the world, and the trek is going to completely change, right? The beautiful ice and the Khumbu Icefall that flows off that many people go to even see, even if they're not trekking, could potentially be gone. Another example that I want to share is a story from a glacier, Ka Roimato Hinehukatere in New Zealand. This is the Maori name for what some people might know as Franz Joseph Glacier. And its name literally means the tears of the avalanche maiden. And it's based on a Maori legend that describes how Hinehukatere, she took her lover Tuave up into the mountains. And Tuave couldn't keep up with her, and eventually he slipped and he fell, and an avalanche swept him away to his death. And Hinehukatere, she was so sad, she cried, and her grief was so pronounced that the gods froze her tears as a perpetual memorial of her regret and of her sorrow. And so here you can see how this glacier has changed from roughly 1870s to present day. You can see that it has retreated considerably. And we can also think about what that glacier looks like today and how it's going to continue changing in the future. Now, our projections show that in a best case scenario, the glacier will only lose an additional 20% of its glacier mass compared to present day. But in a worst case scenario, in those higher temperature change scenarios, getting up to 3 and 4 degrees, the glacier will lose on the order of 60 to over 80% of its remaining ice. So these glaciers are incredibly sensitive to those changes in temperature increase. And the key point here is that these glaciers, they're not just a water resource or a contributor to sea level rise, but they're also a key part of the culture and spirituality of many communities around the world. As one Maori individual named Na'alisa Tumahe, she said, it's more than just a physical loss. It's a spiritual depletion, a depletion of our ancestral heritage and a devaluation of our past. So I want to leave with one closing thought, and that's that our glaciers, they tell us a story, and we have the chance to make a difference and write their future story, right? They tell us a story both of climate change, but they're also literally embedded in the oral traditions of many communities around the world. In order to make that future story a positive one and be able to maintain those cultural importance, we need to limit the temperature increase to 1.5 degrees and preserve our mountains and reduce the impacts in the future. Thank you very much.
Thank you, David, for insightful presentation about the global glacier loss projection. Also, you gave like insightful information about like glacier from the different part of the world. So I would like to open floor if some of you have like some question to David. Yeah, please.
Thanks, David, for this compelling motivation to stay below 1.5 degrees. I was interested in it early on. You were showing some of the projections that the uncertainties of the projections were skewed to the high side, and they also scaled with the amount of warming, those uncertainties. Can you just talk us through why that occurs?
Yeah, so I'm not sure exactly. Are you referring to the uncertainties through 2100 or 2300?
Yeah, 2100. It was really early slides. Yeah.
Yeah, so even through 2100, I mean, there's so the temperature change scenarios, right, that we're aggregating are based off of global temperatures, right? So the global mean temperatures. But what we know through Arctic amplification and even just the mountains in general is that these glaciated areas are going to experience different amounts of temperature increase compared to that global mean temperature. So that's one of the major reasons why you have a considerable amount of uncertainty, is because the sensitivity of these different regions to the global mean temperature increase can vary depending on the different general circulation models that you use. And in some regions that have a lot of precipitation, specifically those that are close to the coast, for example, Iceland's a great example of this. The amount of precipitation that's projected in the future really varies depending on the GCM that you're using. And so the combination of the differences in precipitation and the differences in temperature can have you get a lot of uncertainty in those projections when you look at the temperature change scenarios. But that uncertainty, even though there's considerable uncertainty in exactly where it is, the story is still very clear as to the differences between the temperature change scenarios.
Hi, David. Sian here from University of Edinburgh. My question is about the rate of warming and what difference that would make to the rate of glacier loss. So we're stepping outside the SSPs now, but does it make a significant difference to the mass loss if warming is much slower, but still happens?
Yeah, so that's a great question. And I know there's some ongoing work that's starting to look at this question. So hopefully in the next year or two, we'll have a better quantitative understanding of that. But yes, if the glaciers, right, they respond very slowly to increases in temperature. And so if you start to increase the temperature a lot, and then let's say you start to bring the temperature change down afterwards, the glaciers, their response times mean that they're still going to be responding to that increase in temperature for decades, to even for larger glaciers, they can have response times that are hundreds of years. And so you're going to have a lot of mass loss that's already baked into the system. And that's also part of the reason why that sort of beyond 2100, when you start to get to equilibrium, part of that is because the present day mass change is needing time to level itself off. If you're able to more slowly increase the temperature, then it allows the glaciers to try to find a new equilibrium a little bit faster, because you're not perturbing the system to the same extent. So yes, the rate of temperature change is certainly important. Yeah, great question.
Thank you.
Anyone else? Yeah, I have one like very common question. Yeah, you have already mentioned about like uncertainty. So like, yeah, once the glacier will start to melt and they will like retreat at high elevation too, like once they will be in the high elevations, still there will be like high temperature and they will melt at the same rate, or is there will be like some decreasing rate of melting at high altitude of mountains?
Yeah, that's a great question. So the elevation melt feedbacks, those are incorporated into our model, or the elevation retreat feedbacks. So that is captured where as the glaciers retreat to higher elevations, they're obviously trying to find colder temperatures such that they melt less. What does get a little bit tricky here, right, is we're using a simplistic model, right? We're using a temperature index, or sometimes called a degree day model, where the amount of melt is just parameterized as a function of the air temperature. And so when you get into some of the higher elevation ranges, sometimes you get into areas that might be in steep topography. And so the solar radiation and really the shadowing from the surrounding topography could have an impact, right? And an energy balance model, a distributed energy balance model that accounted for the actual position of the sun compared relative to the mountain and the ice, that would be able to capture that, while our model, it's a 1D model that does not capture things like that. So it's possible that as these glaciers retreat to higher elevations, that shading or even things like avalanches from surrounding terrain that we don't explicitly account for here, that could help, but it's a pretty tricky question to answer, just because we don't have a lot of the other data sets that we need to be able to parameterize a more physically based model at the moment.
Yeah. If you have more questions, yeah, please.
Just one more from me. So David, when you're forcing it with the climate model, does that mean that the climate's pretty smooth over time, or are you capturing the weather, the natural variability in the system? And I presume, because effects can be non-linear, that actually that short-term variability actually really matters in the system.
Yeah, great question. So kind of a two-part answer. So one is that we are using those climate models, and most of the GCMs, they produce data that's readily available at a monthly resolution. So we do force our model with monthly air temperature and precipitation data. So when you get to the monthly scale, you obviously have a lot of smoothing that's already occurring. All right. So we're not capturing, right, in some cases, extreme heat waves that we saw over the last 2 years in Central Europe, for example, right? The GCM is not going to predict those extreme heat waves, right? So there are feedbacks associated with melting, extreme heat waves, albedo that could change how the glaciers would evolve in a very localized perspective to that natural variability that you mentioned that we're not capturing. We are starting to look at the impact of moving to a daily resolution and seeing how that affects it. But then again, we're still using a climate model. So it's not a reanalysis data set that's going to capture the heat waves that we've seen in present day or in recent history. That said, we do capture a lot of the natural variability by running large ensembles. So for this, we're running for, I believe, every SSP had 12 different GCMs in this study, and our group is currently running just large ensembles where you have over 50 ensemble members for a given GCM, such that we can quantify the uncertainty associated with just that natural internal variability. So on the one hand, we are accounting for that variability, but on the other, we're not capturing, specific weather-related events, as you mentioned.
Yeah. Any more questions? So yeah. Thank you, David. Thank you very much. You made it all the way from that. You are here, but you're back US and have a great time there. Thank you very much. Looking forward to see you again some here. Yeah.
Likewise. Thank you very much for having me.
Yeah.